I'll start by saying thank you all for being here. This is the second online seminar organized by IIWER, and as we have the kind support of PNNL today with especially the Zoom license, because there's a lot of you. We also want to thank very much Professor Simon Neal for contributing and making this second seminar happen. Today's presenter is Dr. Zhaoqing Yang. He's a chief scientist at the US Department of Energy in the Pacific Northwest National Laboratory and a distinguished faculty fellow at the University of Washington. Dr. Sorry, I think I was muted by some reason. So Dr. Yang's research covers a broad area, starting from coastal hydrodynamics to transport processes and their responses to climate change using state-of-the-art numerical models. His recent research focuses on marine renewable energy resource characterization and assessment and the impacts of extreme events on coastal zones. Dr. Yang is the editor of the book Marine Renewable Energy, Resource Characterization and Physical Effects, and a member of the Editorial Board for Renewable Energy, the International Journal of Marine Energy, the Journal of Coastal Research, and the Journal of Marine Sciences and Engineering. He holds a PhD in Physical Oceanography from the College of William Mary in the United States of America. So before we start the presentation of Dr. Yang, I would like to ask a favor by all the participants. Please mute your microphones. At the end, we will have questions. So please try to keep any questions that you would like to ask for the end. And we will have about 15 minutes of questions. Those can either be by raising your hand or simply typing it on the chat, and we will try our best to convey them to Zhaoqing. So I will leave you to it. I hope you will enjoy the talk.
Okay, thank you, George. First of all, I would like to thank the organizers of IIWER group, for inviting me and give me the opportunity to share some of our work we are doing in US on the wave resource characterization. So I really think this is a excellent forum, right, for the communities, especially in the wave renewable energy and wave energy resource characterization, and to share, information and what we learn, and especially towards a goal to standardize or try to come up to support the international standard development. Okay, so yeah, today I'm going to talk about wave resource characterization at the regional and local scale using a multi-resolution modeling approach. Here's the outline. First, I would like to give some background of our modeling effort, and then follow with some discussion on the approach and the challenges. Okay, why we take that multi-scale and the multi-resolution approach, and then I will show some examples from different regions in the Pacific Ocean on the resource characterization, and finally I would like to share our strategy on the data dissemination. Okay, and some summary and the future work. So first of all, I would like to share an image. Actually, it's recently published in a report by NREL, the National Renewable Energy Laboratory. I'm not going to focus on the numbers because the number is going to be updated very soon. This is based on a serious resource assessment about 8 to 10 years ago. Okay, so from 2011 to 2013, the U.S. Department of Energy Water Power Technology offices support a 5-study individual, 5 studies to look at the resource. Okay, and the key image, I mean, key message here is the wave, the light blue, actually, you know, composed most a percentage of the marine renewable energy. Okay, so that actually leads to the question. Okay, the first assessment, is that enough, right? How can we refine this number, especially in a nearshore scale? Okay, because ultimately we want to, why we want to understand the maximum potential of the resource, but we also want to know, okay, how this measurement or model handcast can support WEC development. Okay, so so with that mission in mind, DOE funded multi-year, multi-lab signature project, okay, on resource characterization, model validation, and classifications, which in general cover tide, wave, ocean current, and also river, hydrokinetic, and ocean thermal. Okay, so NREL is the overall lead and also lead to the measurement of the project, and the PNNL lead to the modeling effort, and Sandia National Laboratories lead to the classification and also providing support on the modeling side. Okay, so there's a link on this project. Now we talk about, I mean, the previous study. Okay, it's actually based on NOAA's hindcast with a resolution. The highest resolution is 4 minutes, 4 arc minutes, so which is several kilometers. Okay, so that's too coarse, especially in the near shore. And also that study actually only cover a few years, so actually less than 5 years period. So it's not long enough. Okay, so especially if we want to look at the annual and the seasonal variability. Okay, so and also DOE want to really to look at a broader region, especially cover all the U.S. exclusive economic zones, the EEZ. So this image shows the EEZ domain actually of U.S. right. So most of them in the Pacific Ocean, and also this part in the Atlantic, the Mid-Atlantic, and the Gulf of Mexico, and Caribbean seas. Okay, so PNNL actually covered the Pacific Ocean, which I listed, highlighted as a blue, the West Coast, Alaska, Hawaii, and the Pacific Islands territories. So that actually there's 7 individual regions over there. So to do so, because this is a large domain, right? So, and we think it's very important also, if we want to do any nearshore high resolution model, we need to have a spectrum open boundary conditions. To provide that, we need to run our own model, okay? But we are not, well, I shouldn't say run our own model, we need to run the global model. So in collaboration with the NOAA, we actually adopt the NOAA's a 3-layer, 3-level WaveWatcher 3, okay, model. The existing NOAA's model, the global model, does not cover the 7 Pacific Island territory, okay, with the 4 minutes grid. So PNNL actually add the 4 arc minutes model for the Pacific Islands, so that to these multi-scale ensembles. So we were able to, that way we were able to provide, I mean, higher resolution open boundary conditions to drive the nearshore swarm model. So this is the domains, okay, we are currently working on within PNNL, okay, is the Pacific Ocean regions. So I'm not going to go through the numbers, okay, but it's basically cover about 80% of the EEZs of the US, okay. So it's a large domain, and I will share some information about, the computation need and those, okay? Next. So I mentioned about the multi-scale, multi-resolution approach before, okay? So, and again, the reason is so that we have a good control of the open boundary conditions. So the global model is from WaveWatch 3, adapted from NOAA. And we also use the unstructured SWAN model because really, we feel in order to simulate the details of nearshore wave climate, we really need to take the unstructured grid approach, okay? So we roughly, because of this triangle, right? So we can't really say a specific number of the resolution, but roughly it's about 200 meters. So actually, if you refer that to a rectangular, actually it's even smaller, right? Because if we look at the area of a cell, it's smaller than a rectangular of a 200-meter size, right? So, and we conduct the extensive model validations, okay? Not just the wave buoy, but also satellite data. So, and for the wind, actually, we just continue use the CFSR, which is a product from NOAA. Okay, it's a global wind product. Okay, so this on the right is an example of our wave on the west coast with a wave buoys. So that actually for the west coast, we have a very good data set for from the deep water to shallow water areas. So actually, in some of the areas when we feel missing, it is important, but also missing a nearshore wave data, NREL actually deployed a number of buoys to supplement the observation data so that for model validation. So this is just an example of the model grid, okay? On the left is the West Coast. So it's very detailed, but the relatively West Coast, US West Coast, it's not as complicated as other region, okay? So we were able to go to this, some of the major bays and estuaries, okay? So the inset actually shows the grid of Monterey Bay. There's one actually a wave buoy inside actually shows once we have the high resolution model grid, actually it's improved the wave prediction near the mouth of the bay. The middle panel shows the Alaska, okay, grid. It's very complicated. We have, more than hundreds of islands. So actually it takes us a long time to develop that grid for the Alaska domain. And on the right, it's kind of a similar, it's a Hawaii. For Hawaii, actually, we have even finer resolution because the island is small. And of course, there's other opportunity. We think it's important. For example, the powering of blue economy. So we on purpose to have a higher resolution in the Hawaii region. I mentioned about the standard before. Okay, I think it is important to advocate, for the wave resource characterization. We should always try to tie to the international standard, the technical specification. Okay, so we don't really mean. I mean, you have to meet every criteria, but at least we need to have that in mind. If we do not meet it, why? Okay, ask us. Maybe in that particular region, some of the specification may not be applicable. Okay, but here we try to make sure everything is checked. So all the parameters actually, I think we in this modeling effort we meet, except right now we do not consider CIs. I mean in SWAN. Okay, and wave current and the water levels we are not considered, okay, and we definitely need to improve that in some of the areas. So we are running large domain, right? So we feel, okay, this is a lot more information to take, at least at this phase of the project. So I want to show you a comparison for a model and the refinement model of a wave, a swan in comparison to NOAA's wave watches radar for arc-minute model. Okay, so on the left is the wave watches 3 model, and along the west coast, actually zoom in about the Grace Harbor. It's actually is in the I believe that's in the Washington coast, and also on the right is Alaska. So you can see with the high resolution, actually, it's not just give you more information, but actually it can resolve the wave propagation much better into the nearshore region. So that's why actually the information is, if it's a high resolution, it's much more accurate. Okay, so we actually in the publication also shows that in a comparison with the NOAA's model. NOAA's model, I just want to emphasize again, it's excellent. Okay, so it's not because they are not good, but it's just in some of the shallow area because of the limitation of model resolution, it's not able to capture some of the details. Okay, so based on the IEC standard, okay, we actually I think many study nowadays also try to compute the 6 IEC wave resource parameters. So all the study, all the domains, we actually calculate those 6 IEC parameters and compare to observations. So observation, of course, when we talk about the data, we need to have a high-quality spectrum data to calculate the IEC cylinders parameters. Okay. We also, I will mention actually, show you later too. So, but through this effort, we actually coded the model output for the IEC 6 parameter inside SWAN and wave watches 3, so that you don't need to output the spectrum data at those buoy locations and then to calculate the IEC parameters outside. Okay, so it's a direct output now, and we are happy to share the code with the community. The other things I think it's important for model validation is the spectrum comparison and also bivariant histogram. Okay, so this is yet another example on the West Coast. So for the 2D spectrum, as you can see here, on the left is the data in summer and winter. On the right is the model. So I wanted to point out that in the summer, for example, in the upper panel, the model was able to capture, even though it's the signal is small and the energy level is low. However, it's important to capture some of the signal the swell actually propagate from the Southern Ocean. Okay, so I don't know whether you can see my cursor here. So this tool, right? It's we were able to simulate that, and of course in the winter it's mainly dominant as well from the west. So and also the bivariant the histogram, it's important to capture, especially what is the high frequency areas actually that to use to design or to guide the WEC development, and also what is the probability of extreme. Okay, so for large wave. So this is important, so to compare the model and the data. Now I mentioned about the importance of high resolution for nearshore resource characterization. Okay, so this is an example I would like to show you. So in the West Coast, we pick 2 points. It's about 10 kilometers apart. And you can see on the left, is I believe that, okay, it's the optimal, yeah, that's the wave power density, right? So there's a hotspot in this area, and just south of it, about 10 kilometers, and actually it's a cold spot, which means, you know, you don't actually have the same level of wave energy. Actually, it's the opposite. And that also shows in the power density, I mean, the power rows plot, okay? And also similarly, you know, you can see the difference in terms of variance histogram, okay? So the high resolution allowed us to identify the hotspot or cold spot actually in the nearshore region. And the other thing is, I think it's important is to look at the petitions sea state. Okay, so in our study, we basically look at the 6 sea states. Okay, from wind sea to wind sea, and a combination of wind sea and the swell, and also single swell and the multiple swell. Okay, so this gives you the insight of, okay, for example, in the winter, it's mainly dominated by the swell, okay, 2 swell system, and also 1 swell, okay, like the orange and the reddish. However, in the summer, it's mainly dominated by the 1 swell and the wind sea, okay. So these are the, I mean, very important information again, yeah, for the WEC development. If we look at the further, now we only look at the 2 bimodal sea state. Okay, one is the wind sea, the other is a swell, and we can see it's very distinct pattern in along those 4 locations. Okay, so in the northern part, we can see a mix of wind sea and swell propagate. Okay, the swell actually always pretty much from the west. However, we do see wind sea from the northwest and also the southwest direction. But down in the California, especially southern California, you can see actually swell propagate from the south, and that's mainly from the Southern Ocean. Okay, so so we think that's, you know, it's important to look at the petition, okay, and bimodal sea state, and we also have a recent publication in the Hawaii Islands. So it shows a very, very distinct feature, okay, when we have a petition output. So seasonal and the decadal variability. Okay, I think most of you are very, very familiar with the seasonal variability, right? So in general, but I would like to point out that with the 32 years of simulation, we were able to capture some of the signal in the decadal scale. Okay, so this is wave power anomaly. Okay, in compared to the ONI index. Okay, so that actually those are 3 peaks corresponding to nicely to the 3 El Nino events. So we haven't really spent a lot more effort actually looking into the detail of other regions yet, but I mean, this is something actually would like to continue to look at in terms of the climate variability or correlation to that. Okay. I want to share something actually on a so-called lesson learned. Okay, so we started the West Coast first, and then we started to simulate the Alaska region. And when we look at the power distribution, and we notice very evident the garden sprinkler effect. Okay, around the Aleutian Islands. Okay, so there's 2 approach to mitigate the garden sprinkler effect. One is, you know, you increase the resolution. Okay, the directional resolution, not the grid resolution. And the other way, it actually you smooth it. Okay, by causing the model grid resolution, which is not what we want, because we want a high resolution in the near shore, right? So in order to do that, we actually starting from the 15-degree directional resolution and reduce down to, increase the resolution to the 5-degree. And we were able to mitigate the garden sprinkler effect, but that also increased the computational time significantly. It's basically almost 3 times, right? So, and because of that, we already finished the first round of a West Coast simulation, and we will look at, okay, let's look at the the canyon area in the Southern California, and then we found that, okay, there's also evidence of garden sprinkler. If for example, in this area, right? So that actually the ray actually always, propagate all the way to the coast. So we actually also increase the directional resolution, and also reduce the time step in order to capture.
I'm so sorry to interrupt, but may I interrupt?
Yes, please.
Because I'm sorry, but at least I'm not able to see your mouse. And also, could you just explain what you mean by garden sprinkler effect?
Yeah, so when we propagate and the wave and let me use this. So it's basically the wave array that propagate around the islands, and then it's a numerical, right? So it's a start of the wave because it's artificial and propagate all the way in that's the artifact. So in order to resolve that's the reduce the numerical error, so we have to increase the directional resolution of the spectrum. Okay, so that's why, and if you compare these two, and you can see more clearly. So then this array is artificial. Okay, and if we zoom in the Alaska, it's even more. So, and there is a time series too. So actually, in one of the very near shore station, actually it shows improvement in terms of the hindcast compared to the data.
Okay.
Okay. Consent. Okay. Thank you. Because of the time, okay, I'm going to quickly go through this these are the details, but I also think it's important for people are actually doing the wave hindcast. Okay, so now the model really take a long time to run. Okay, so we look at some resolution. Okay, so we look at the swell propagated, for example, around the Hawaii Islands, and we found, 10 minutes resolution, 10 minutes time step actually would not able to capture properly of the arrival time of swell, okay, compared to data. So this is period, okay. So even though when we calculate the error statistic, if you look at all the line, actually it's aligned with the data quite nicely, but the arrival time was wrong, okay, with the 10 minutes time step. So when we reduce the time steps down to 2 minutes, actually it's get much better match to the data. And because of we have a much finer time step, and we will hope, okay, in that way we can also reduce the solution iteration, maximum iteration. Okay, so and this is just example to show that actually most of more than 99% of the iteration actually converge within 2 time steps. So, and this time series just shows actually is you don't even can see much difference, just 1 time step or 2 time step. So with very small time step, you can get to the physics right, but you can, on the other hand, actually you can also save some computational time. Okay, so we basically for this particular application for the Hawaii, we actually use 1 time steps, but with much smaller time steps. Okay. Now, nearshore hotspot identification is important. However, how to do it in a large domain? So we use Alaska as an example. Okay, so one thing we want to avoid is too much monthly variability. Okay, this is the top figure shows if you have too much monthly variability, that's probably not ideal. Okay, the other parameter is more important. A parameter is a function of the wave power and divided the variability, monthly variability. So when you have a bigger optimal hotspot identifier, then it's more ideal for the WEC development. And you can see some hotspot, more red in this area, and also some area, especially southern part of the Aleutian Islands. Okay, so this is something I think we, at least from PNNL's work, is the first time we applied this, and we find it's quite useful to provide, large data set and to the developer for them to look at into in detail. Wind is important, and because of time, I'm not going to go to the detail, but in this case for Hawaii, because we are leveraged, I also want to really, just for the purpose of this this group also, right? So the purpose is we want to collaborate, right? And then we collaborate with each other. So for this particular project, we for the Hawaii domain, we actually collaborate with University of Hawaii because they have an operational model with a dynamic downscaling wind, okay, around the Hawaii Islands. So we use that wind product. And actually, there's a noticeable improvement compared to the NCEP, the CFSR. The other example, which is not as a part of the wave resource assessment, is in the Cellar Sea. We've recently also published a paper on that, is to also use a WRF downscaling. It's a 5-kilometer resolution wind, and it's significantly improved the wind product. And of course, it's also improved the wave prediction inside the Puget Sound and also Cellar Sea. One thing I want to mention about is the data. Okay, I've been reviewing quite a lot of paper on the model validation or model hindcast for resource assessment, and the validation is something I always want to check, right? So we all want to check on that, but measurement it's hard. Measurement data is hard to get, right? And it's expensive, and that's one of the reasons that we use model. However, in the case you don't have data, what are we going to do? So satellite actually provide another option, at least at the broader scale, and cover the entire model domain. Okay, so this is the left figure shows the 3 wave buoys in Guam, the Pacific, one of the Pacific Islands territories. Actually, before 2010, we only have 1 buoy available. Data available. That's the 121, number 121, right, in the southern part. So for the past 32 years, hindcast, we only have 1 buoy data. So we decided to look at other data set. Okay, this time series actually just shows our recent simulation for the most recent 10 years of simulation. Okay, so it just shows a good comparison, but I want to show you the reason we feel comfortable that the model is being developed, or validated properly, is we actually use satellite data for all the 7 regions or 7 areas of the Pacific Islands territories. Okay, so this is the data set actually from all the satellite data we compile, and also the number of observation points within, for all those regions. Okay, and let me show you some data set comparison. Okay, so we have a significant wave height only, right? So we just calculate the root mean square error, the correlation coefficient, and the bias, and so it gives you, I mean, an overall idea or look how the model performance at, you know, in the model domain, and also, you know, list the data density for the entire domain. So we at least have several thousand for each of the 0.2 degree beam. Okay, so so I mentioned again the IEC standard, right? The 6 IEC parameters. So with that, we actually developed and output those parameters for all the regions. So this shows the monthly variability, okay, in the West Coast between winter and the summer. So I'm not going to the detail of those, I mean, in terms of characteristics, but you can see it's a dramatic difference in the northern, I mean, North Pacific Northwest, but the variation is, in general, is much smaller in the Southern California. Same thing, we also doing that for Alaska. I mentioned about in Alaska, we actually do not have the way, I mean, the swarm domain cover the northern Alaska and the Arctic. So we actually implemented in the source code to output the IEC parameters. When we run the global, I mean, the 3 level global and the regional wave watches 3 and the output that. So that's actually is 2 pieces of data sets merged together. And similarly, we can do that, I mean, for other regions, right? So this shows the monthly variations. The previous one is just one, is the 32 years of average. So we can do all these seasonal, monthly or annual average, okay, for the model domains. So model outputs, okay, the latest slide, I also have those information, but we have a 6 IEC parameters cover the entire region. We also have a spectrum output at the locations with a specific distance from shore, okay, at the hourly interval. So the distance from shore, it's vary from domain to domain. It really depends on, you know, the region, right? Because some of the area has very steep or very narrow continental shelf, and then the water depths, you know, become very deep very quickly. So then the output, then we probably will have a more focus, more near shore, okay? But for other region, it would be different. So this is just an example of Alaska and one of the Pacific Islands. I think that is American Samoa, okay, on the right. So we also output the spectrum data along as some specific isobars. Typically is at the 100-meter isobars, okay? So a lot of data and being output, and the storage, of course, it's also expensive. I mean, a large storage is needed. This is just an example, actually. Once we generate this huge or rich data set, we can use that to support the various application, offshore application, right? Such as the PPE. And this just shows you, especially for the remote community in the Pacific Islands or Hawaii Islands, right? So because it's island and the wind wave is completely driven by wind, right? Of course, it's also affected by the geometry, but the driving force is wind. So around the island, even though it's a small, this is a Maui, and you can see that actually the climate, the wave climate is quite different from location to locations, okay? And the data set that we provide will be very useful for, I mean, for the industry. So if they are interested in, you know, harvest wave energies around the island. And the line plot is just average at the 5 kilometer from shore for all those islands, okay, the Hawaii Islands. So okay, and we output a lot of the, I mean, run the model, and now we have 32 years of data, right? And ultimately, we want to share those data with the community, right? That's the goal. It's not, I mean, sure, everyone likes to do the science, right? So it is interesting, and it's definitely a motivation behind that also. But the ultimate goal is to share the data and the support, right? And the energy, industry. So right now we NREL, okay, is taking the lead on the data assimilation, data dissemination effort. So right now the West Coast and the East Coast and also Hawaii data are actually available online, okay, which cover the IEC parameters for the entire domain at the 3 hourly interval, and also directional spectrum at the virtual pooling. When we say virtual pooling, means what I mentioned before, basically at those locations with a specific distance from shore, and also actually at all the buoy sites. And for any locations we have a buoy measurement, we also output the model result, so that anyone want to look at it further again, comparison, the data is there. Okay. So it's a 32 years, but we are this year we are actually doing extended the model hindcast from 2010, to 2020 now. So we are doing the last 10 years of simulation from 2011 to 2020. Okay, and the other region, such as the Alaska and Pacific Islands data for the 32-year hindcast should be online anytime soon. Okay, so the data, everything is completed, so it should be online very soon. So, and also it will be also on Google Cloud and the Amazon Azure platforms in the future update. So we just try to make it, available to the public the best way we can. So we so this slide again is from NREL, and this shows how can you access to the data set and by register. There's a link there. So again, I'm not going to go to the detail. There is one webinar, so please just pay attention to to the announcement. That the announcement should come out soon. Okay, it's next month, end of next month, on the new marine energy atlas. So a quick summary and the future work. Okay, so we have generate 32 years for wave hindcast at the regional and the local scale. So this image, actually the globe image on the Pacific Ocean, shows the 32 years average of wave power. So at the high level, at least they give you, okay, what is the wave energy level looks like at those regions, right? So like I said before, we extended through 2020 now. So by end of this year, we should get that done. Continue to model improvements, of course, and one is the extreme or large wave prediction. That's always areas, especially for WEC design, right, or classification. The other is a wave current interaction. I think that's important, especially in some of the area with the co-occurrence of tidal energy and the wave energy, right? So both are important. And sea ice effect, especially in the northern Alaska and Arctic, we haven't covered, in these regions. So, of course, the other is the climate, but that is pretty much like a side product. Once we have 40 years hindcast, I think it's a long enough record, to look at some climate effect. Again, wind is important, so I really want to highlight this. So ultimately, it's wind, controlled everything. So try to look at the data set, in your region, if there's any downscaling. A lot of universities actually, they have their own operational model, right? So utilize that and to improve the hindcast, and also look at, the community, international agreement for any new product. So, and again, here's the NREL's webinar informations. So with that, I think that's all. A few minutes pass, but I'll be happy to take any questions.
Thank you, Zhaoqing, for the very interesting talk. It's interesting to see the involvement of so many data sets globally. So we have around 15 minutes, let's say, for some questions. So please feel free to either raise your hand or put them on the chat. So can I ask first something that it was in my mind?
Sure.
Did you try the differentiating the wind growth components to see if you would get a different swell representation instead of using the common scheme, using a bit something more, let's say, linear?
No, we haven't tried, but yeah, I think there's something. You're talking about the partition, right? So there are the different scheme. We understand. So to separate the different swell sea or wind sea component. So I think we haven't really looked at the different scheme and how different it is. So, but with the scheme we are using now, especially in the comparison to data, it seems to work quite well. So, and I also understand, in general, you can have even more, right, partition group. So, and so it really depends on the locations. So some maybe even have more, and if you like to look at those. So, but right now, we have a 6th group, and everything, if you cannot separate in the first 5, and the rest we will group is as others. So.
Thank you. So just to make, because my chat went down. So Dr. Hassemi wants to ask something. So please, you can unmute yourself and ask. Dr. Hassemi, we cannot hear you. Yeah.
On mute or something, seems to me.
Yeah. Dr. Hassemi, you can type it on the chat and we can pass it over if you want.
And then I want to share another information while we are waiting for waiting for our questions. So is the computational demand. Okay, so roughly for the domain we have, I presented in the Pacific Ocean. Okay, so it take about 1 million. Yeah, 1 million CPUs for a 1-year simulation or one. Yeah, so so it's a lot of a CPU too.
So another question is, what is the resolution for the nearshore resolution of the model?
Yeah, that is about it varies. So it's about from vary from 150 meters to 250, something like that. So roughly, because it's about 200 meters of resolution.
I think there was a hand up, but Khalid, you had a question, if I'm not mistaken.
Yes. Thank you, Dr. Zhaoqing, for this presentation. My question is about the comparison between spectral wave measurement and spectral estimation.
Yeah.
There is a plot on which you compare the spectral data measured by Boyce and the one estimated by SWAN model. Mm-hmm. My question is about when we try to compare these 2 parameters in the Boy, we found that the Boy has more division on spectral game, spectral frequency number, and more than SWAN, doubles. Like SWAN can have 30 to 35 division, and the Boy measurement has more smaller range of frequency considered, and also in directionals. When we compare the direct plot, did we make an interpolation, or how we can do this to get a real comparison?
Well, my recommendation is, yeah, if the data will have a more frequency beams or direction, right? So then the model, I would just average it with the resolution of your model, instead of interpreting it from the model to the measurement. So I don't know whether
in Swan models, there is a limit. They are recommending that the number of beams or class that we have to make should respond to some criteria, and the maximum that we can arrive to is 35 beam on frequency time, and on direction maybe we can absolutely, as you say.
Yeah, I would surprise. I don't know whether there's a limit on that. Of course, we never run. I mean, it's even higher than that. But I would, yeah, I would not. Yeah, I think that should be a problem. So I mean, in terms of limit of the frequency being so.
So another question by Dr. Hassemi came through the chat. So he's wondering if the wave modeling product is also useful for the design aspect, especially for instance of extreme weather events, because some of the models that exist out there, some of the wave models, show a very poor performance in extreme conditions. So basically they underestimate a lot, while they are good for wave resource characterization. So what do you think about that?
Yes. Actually, I think that's leads to a question about or a separate effort actually led by Sandia National Lab, right? They try to look at the classification of the wave climate for the environment, but also for the device conditions. So that actually is just look at especially look at the extreme events, and so that would be useful for the WEC design. So that it's not my expertise, but I understand that is what the purpose of the HICAS data used for, right? It's ultimately to classify, okay, in what environment actually is more suitable for what kind of device design. So yeah, so to answer the question, the answer to the question is yes. So especially you have a spectrum data, as far as that's very, very important. So.
Thank you. Is there any other questions? Somebody wants to type something, or yeah, HP. Sorry, I don't know the name, but you can go ahead.
Okay. Okay, please. I would like to know the swarm model. I don't know how, in the conception of the grid, how do they consider the ER like Island? Island, are there specific way to characterize to Island? And the second question, I saw graphics, winter and summer, comparison between wind and wave, the direction. I would like to know for the second graph. I think it was the period of the summer, when the direction of wind and the other one, the direction of wave, they were not the same. How can be physical? How the physical explanation of that graph?
Now I want to go back to, I don't know which specifically.
It was a comparison of the wind and swell during winter and summer.
So first of all, about I don't think we have. I don't think we have a wind or wave comparison for American sonar. So I don't know which one. But to answer your question, so can you repeat the question about the model grid? I actually don't quite understand about your question about the model grid.
Yes, the model grid is there during grid generation. During grid generation, how do they take account Island?
The islands, Zhaoqing, how
Island.
did
the
grid generation
island,
module,
okay.
yeah, took into account the islands.
So
Yes.
yeah, there are many
Island.
there are many grid generation tools. Okay, the one we use it's called the SMS, it's a surface modeling system. So basically, you provide the contour polygon of the island. Okay, any land boundaries,
Okay.
and then you specify you basically along the polygon, you basically specify the grid interval you desire. Actually, it can be varied, and the system will automatically generate the grid. Of course, there's a lot of manual improvement or check it will be need to be done. But yeah, the SMS is one of the tools. I mean, a lot of people use, but there are also, I know, people also use their own grid generators. So I wasn't sure which actually image you are talking about, the comparison of a wind and a wave. So because it seems to me talking about a specific. So this is the slide which has a wind and the wave is on the Hawaii Islands. Okay, so not sure if you are.
The graph, the graph, they were inside. They were inside a circle.
So just to speed things up, because we only have one more question that's been on the chat, so let's do that, and you can follow up once you know. You
email
find
me.
the figure. You can email Dr. Yang. Yeah. So somebody's wondering whether the model can be used in operational prediction. The question is because, as you said, it's very expensive to run. So do you think that your model can be used as an operational prediction model?
I don't think that this particular model, I mean, the one we have developed is used, I mean, it's practical, right, in terms of operational, because the runtime is so expensive, right? So, however, the approach, I think, can be adapted to operational mode. Okay, so for any smaller domain, then you can. So I think that's I think that's a good idea actually. If you want to look at some of the wave climate in a smaller domain, and then operationally you can actually adopt. I mean, NOAA's right open boundary, or you can run NOAA's open boundary. I mean, so because of a proper open boundary condition, it's needed. But then in the fine resolution, people have done that. I mean, so. Either use WaveWatch 3, WaveWatch 3 also start to have their own unstructured grid model now. So, but the approach, I think it can be adopted for operational.
Thank you very much, Zhaoqing. Thank you very much for taking the time today to show us this very interesting work and the upcoming Wave Atlas that improves upon previous work. All of you, thank you very much for participating. And on behalf of Bahari Kamrazad that couldn't be here today with us, and the IIWER group, from myself and Adem Akpinar, we would like to thank you for participating in this series on seminars online for wave climate and energy. And we really hope to see you soon again. So thank you all.
Thank you.